Alright, well, welcome to Lecture 18. This lecture is on complex numbers and roots of unity. So what I want to do in this lecture is just briefly review how to work with complex numbers, especially to review what's called the polar form of a complex number. And we'll see how that straight away leads to some of the more interesting calculations which are perhaps less known outside of like math majors. Now, but certainly everything I'm going to tell you in this lecture could easily be taught to high school students, and indeed classically has been in certain regions. So anyway, here it is. A complex number has the form x plus iy, where x and y are real numbers. In that case, x plus iy is called the Cartesian form of the complex number. The complex conjugate of z is x minus iy, and we use a z bar here. Sometimes physicists or other folks will use a z star, but we'll use bars here. Now the length, or absolute value, or sometimes called modulus of z, is this z between these vertical lines here. And so that's the length of the complex number, in the sense of that's how far it takes to go from the origin out to the complex number, like that, right? So just to give a little picture that makes sense, because if this is z, which is equal to x plus iy, that means that this distance right here, you can see this right triangle which has length x and length y here. And if you were to go into the other quadrants, then you could replace that with absolute value of x and absolute value of y for the lengths. And you know, that is why that formula makes sense. It's the distance from the origin to the complex number x plus iy. Now, both the conjugate and the length functions have very nice properties. Here they are. The conjugate of the sum is the sum of the conjugates. Conjugate of a difference is the difference of the conjugates. Conjugate of a product is the product of the conjugates. The length of a complex number is the square root of the product of it and its conjugate. And finally, the length of the product of two complex numbers is the product of their lengths. So this is actually a very important property, number 4, and it's part of what makes complex numbers so very special. In my own personal research, I've done a lot of work over what are called associative algebras. And in a general associative algebra, even commutative algebra, there really is no expectation that the norm of a product is the product of the norms. Usually this gets replaced with an inequality less than or equal to some multiplicative constant times the product of the norms. And that pretty much ruins the analysis for calculus built over an algebra, say, versus complex complex calculus. But anyway, that is really not this course. So here's the proof of one. Your z and w, add them, conjugate them, and you see that we get that is equal to that. And the proof of all the other items here is really straightforward calculations, quite enjoyable. Z times w is this. You conjugate it, you get star. Z bar times w bar is that. And if you look at star and star are the same, therefore z bar w bar is equal to zw bar. And likewise, zz bar is just straight up x squared plus y squared. So that tells you the length of z is the square root of zz bar. And finally, if you use 2 and 3 together, you can get 4. So the length of zw is the square root of zw bar, which is the square root of zw z bar w bar, which is zz bar times w bar, which is the length of z times the length of w. All right. Anyway, so that's just the basic stuff, yeah? Now, so let's talk about the polar form. All right, so for theta real, we can define e to the I theta, the so-called imaginary exponential, by cosine theta plus I sine theta. And so for z is x plus iy, we have the modulus of z times e to the I theta, as it turns out. That's equal to r e to the I theta. If we write z is equal to r e to the I theta, we say it's in polar form. Really, it's the magnitude times the direction. E to the I theta is a complex number with length 1, which points in the direction in which z you find z from the origin. Here's a picture. Here's some supporting calculations. So if I put z here, if I look at it, I've got r cosine theta, r sine theta, for r being the length. But as we said, r is equal to the length of z. So we've got z is x plus iy, which is r cosine theta plus I r sine theta, which by definition is r e to the I theta. All right. Now you can derive e to the I theta equals to that also by looking at the Maclaurin expansion, calculus 2 style, and the power series for the exponential will pop out cosine and sine, and a bunch of terms have an I outside of them. Those are sine, and the ones without the I are cosine. So this is, there's other ways to derive, quote unquote, this relation, but for our purposes, I'm just defining e to the I theta by this formula right here. All right, and e to the I theta is the imaginary exponential, and it's very important, really beautiful mathematics. And here's how it works. The properties of the imaginary exponential: e to the I theta, e to the I beta is e to the I theta plus beta. You also have e to the I theta raised to the n power is e to the I n theta. This is de Moivre's theorem. You can solve for cosine and sine in terms of imaginary exponentials. The reciprocal of e to the I theta is e to the minus I theta. E to the 0 still 1. E to the I theta, we can also notice, has this 2 pi periodicity. If I add 2 pi k to theta, we're right back where we started. And that number 5 is true because, of course, sine and cosine are 2 pi periodic. So now here's the proofs of those properties. Proof of 1 is actually quite beautiful. When we multiply this times that by properties of complex multiplication, we get a minus sine theta sine beta because of the I squared is minus 1. And then everything else here just follows from distributive property. But then this is cosine of theta plus beta, and that is sine of theta plus beta. So, wow. So in other words, then we get back to, well, e to the I theta plus beta. So what this means is that property number 1 here of the imaginary exponential is a way of capturing both the adding angles formulas for cosine and also for sine in one foul, it's not foul, what am I saying? In one beautiful synthesizing statement. So the imaginary exponential has all of the wisdom of trigonometry at the level of an algebraically natural notation. So useful. It's a tragedy we don't teach these things in high school, because this is not calculus and it could easily be taught to high schoolers. But anyway, the proof of 3 is essentially just if you look at e to the I theta and e to the minus I theta, it's this and that respectively. Cosine of minus theta is cosine theta. Sine of minus theta is minus sine of theta because sine is odd. So when then you add or subtract these, it gives you these formulas for cosine and sine. And I don't really make this, I don't show you how amazing these formulas are in this lecture, but if you're interested, you can ask me. I have other videos that I can show you where I show you how we can use these imaginary exponential formulations of sine and cosine to derive any number of trig identities. So many things we can derive rather than memorize. All right, so let's get a little bit more concrete here. A few examples on how to find the polar form of specific complex numbers. If z is equal to 3 plus 3i, well, the modulus, rather the length of z, is the square root of 3 squared plus 3 squared, which is the square root of 18. If you just graph it, there's 3 here, a 3 here, so that must be a 45-degree angle, which is pi over 4 radians. I should mention, we assume theta is in radians for these kind of formulas, all right? So if I ask you to find polar form, I do kind of want it in radians, but I would be not so upset if you gave me the angle in degrees. Well, anyway, you got choices, but when we write e to the I theta, there's an expectation that theta is radians. I've never seen anybody write e to the I times 45 degrees. It's not done. Anyway, stylistic comments aside, there it is. This is the polar form of 3 plus 3i. Now, who cares? Well, here's why. One reason you might care, if you're going to raise it to the 20th power, raising 3 3 plus 3i to the 20th power would be, I mean, we could do it. We could binomial theorem that thing. We could write Pascal's triangle out to 20 rows, and we could work our way through it. But man, it's so much easier if we just take the polar form for z and then square that and square that, and that gives us 8 to the 10th times e to the 5 pi I. Remember, it's 2 pi periodic, so I can eat that 4 pi I and set it to 1, and that just leaves me pi I. But e to the pi I, by the way, is minus 1. So that gives me minus 18 to the 10th. That's kind of neat. Now, the other thing you could do is you could calculate the reciprocal, like 1 over z. It's 1 over that. And then this is e to the minus I pi over 4, which is this. And then by special, the cosine of pi over 4 minus pi over 4 is 1 over root 2. Sine of minus pi over 4 is minus 1 over root 2, which gives us this. And then the 18 and the root 2 multiply to give me the square root of 36, which is 6. So I get that. All right, so anyway, it's just an example. Next example, a little bit simpler. So I'll scooch it up a bit here. Here we have z equals 3i, so my picture's not great, but it's just on the imaginary axis, right? The y-axis, if you like, right there. So the angle's 90 degrees, but 90 degrees is pi over 2. So, and then here's a check. Like e to the pi I over 2 is cosine pi over 2 plus I sine pi over 2. So cosine pi over 2 is 0. Sine of pi over 2 is 1, so we just get I. So there you have it. 3i can be written in polar form as 3 e to the pi I over 2. Example 3. Here we have I'll move it up a bit here. So here we have minus root 3 minus I, so it's like down here in quadrant 1, 2, 3. All right, so notice that the tangent of this angle I call beta would be 1 over root 3, opposite over adjacent. And if you think about that for a second, you'll see that that's the tangent of pi over 6, which tells me that this beta, this acute angle, is pi over 6. And then if you look at it, that's like pi plus pi over 6, so the standard angle would be 7 pi over 6. So there's the polar form 2 e to the 7 pi over 6. Notice that this 2 is the length of z, which I calculated up here. All right. And then, as an application, if I was to calculate the 12th power of z, rather than taking the 12th power of this sum, which would be a pain, I can just take the 12th power of the polar form, which is easy. So 2 to the 12th is 2 to the 12th, right? And e to the 7 pi I over 6 to the 12th, multiply by de Moivre's theorem. And that gives us 12 over 6, which is 2. 2 times 7 is 14. And that's a multiple of 2, so this is just 1. All right, because that's cosine of 14 pi plus I sine of 14 pi. Cosine of 14 pi is 1, and sine of 14 pi is 0, so this just simplifies to 1. 2 to the 12, so answer 2 to 12. All right, so listen, any complex number can be put into polar form, all right? Now that's not easy in general because the problem is you have to find the standard angle for the number, right? And that's a kind of a sticky wicket, so to speak. That's a little bit of work. I mean, if you teach trigonometry, that's a lot of the course, right? Trying to get students to be able to find the standard angle of a point in the plane. Like that's it's not easy. There's a lot of cases to think about. I mean, it's not that hard either, but whatever. So here's the next theorem. If you have r1 e to the I theta 1 equals to r2 e to the I theta 2, then this forces a couple of things. Number one, r1 has to be equal to r2. I'm assuming that r1 and r2 are non-negative. And also, it doesn't make the angles be equal, but it does make them be what is called coterminal, right? So they're geometrically identical, and they point in the same direction, which means that in terms of arithmetic, they differ by a multiple of 2 pi, an integer multiple of 2 pi. And here's the proof. It's not especially exciting. Basically I just say, well, you take the length of both sides, and that gives you the length of r1 equals the length, absolute value of r1 equals absolute value of r2. But since we're assuming they're non-negative, that gives you that these are equal. Once you know these are equal, then that gives you that the imaginary exponentials are equal, which then says that both sine and cosine of the angles are equal, which forces the difference between the angles to be a multiple of 2 pi. All right. Now this is the most significant jump in this proof, and you can make it more rigorous if you wanted to, but I won't. Now, so here's an application. Let w equal s e to the I beta. We wish to solve z to the n equals to w, all right? So this whole black piece here is a discussion of how do you solve z to the n equals to w when you're given w, right? How do you find such a z, all right? And we're also given the n, all right? So my approach here is to put both into polar form, right? The z which we don't know, r e to the I theta, and the w which we're given, s e to the I beta, and I equate those, and that gives me z to the n, gives me r to the n e to the I n theta equals s e to the I beta, which means that r to the n is equal to s, and n theta is equal to beta plus 2 pi k. Aha, but then that means that since these are both real quantities, that r is just the real nth root of s, and that theta is dividing by n. Theta is beta over n plus 2 pi k over n. And if you think through this, as k runs from 0 to n minus 1, you'll get a complete list of answers. If you go past k from 0 to n minus 1, you'll start repeating answers there. Anyway, so theorem. This calculation in black proves the theorem in blue here. Theorem. The solution set of z to the n equals to w is given by z is equal to the nth root of the length of w times the exponential of I times beta plus 2 pi k over n, right? Where the w is given to be the length of w times e to the I beta. So this beta appears here and there, right? So it's saying that there is a solution. How many solutions there are to that? Well, there are, in fact, n of them, all right? A little bit more notation. Here's a definition that is based on this theorem, basically. So if w is a complex number with angle beta between minus pi and pi, then we define the principal nth root of w to be the nth root of the length times e to the I beta over n. So beta is the angle for w. And then the principal nth root of unity is defined to be e to the 2 pi I over n. And then finally w, the so-called nth roots of w, the plural, there are n things in w to the 1 over n. It's not a function, it's a multiply valued thing, it's a set of values. You have the principal nth root, then you have the zeta n times the principal nth root, zeta n squared times the principal nth root, zeta n to the n minus 1th power times the principal nth root. That's what a mouthful. But these are all the solutions of z to the n equals to w, all right? So these are the solutions of z to the n equals to w. In other words, if I have z to the n equals to w, that implies that z is an element of w to the 1 over n. Excuse me. Here's a little bit more about those complex roots of a unity. So as I was just saying, zeta n is e to the 2 pi I over n, which is cosine plus I sine of 2 pi over n. Whereas all the nth roots of unity are 1 to the 1 over n. There are n things in here. And here's what they look like for some specific choices, like n equals to 2. Oh, by the way, you can write w to the 1 over n is the principal nth root times this set. So like essentially you find one answer and then the rest of them are obtained by like rotating by zeta n or so forth. These are actually just what these accomplish in terms of complex multiplication is rotation. Rotations by angle 2 pi over n times 2 and so forth. And excuse me. Here's a picture. Here's the second roots of unity. Here's the third roots of unity. Here's the fourth roots of unity. And down here's the fifth roots of unity. And here's the sixth roots of unity. All right. And like the fourth root of unity, the principal fourth root of unity is just I, so it's kind of cool. The 1 to the 1/4 is just 1i, I squared is minus 1, I cubed is minus I. The principal third root of unity is minus 1 plus I root 3 over 2. When you square that, you get this actually, so they look like this. Now, I will tell you this, the kind of cool thing about the roots of unity is if you add them together, you always get 0. Like the sum of all of the roots of unity it always adds to 0. I once wrote a paper with a student where we needed to use that in a research paper, actually. But anyway, here's a specific example. Solve w to the 4th equal to minus 1. So to do that, I put minus 1 into polar form. I calculate the principal 4th root of minus 1 is this. Now 1 to the 1/4, as I was just saying, is that. So what I do is I just take 1 to the 1/4 times the 4th root of minus 1, the principal 4th root of minus 1. And when I multiply that, which is this, times those, it gives me these 4 values. These are the 4 solutions, which I've also pictured over here. This is the principal 4th root, and then there's the second one, the third one, and the 4th one. All these 4 numbers solve w to the 4th equals to minus 1. And that's kind of neat, because that means also that you can factor w to the 4th plus 1. It's equal to this times this times this times this, because this, 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 and this are respectively solutions to w to the 4th plus 1 equal to 0. So the factor theorem still makes sense for complex polynomials, and you can do that. Now, of course, this I could also derive straight away from, hardcore, well, not really a hardcore, what am I saying? Relatively simple polynomial algebra. I can write this as the difference of squares, which gives me this, and then use the difference of squares trick again, which gives me this. But then, of course, you run into the trouble, what do you mean by square root of I? Well, we have a meaning for that. The square root of I is the principal square root of I, which is actually e to the minus pi I over 4. Well, e to the pi I over 4 for I, and e to the minus pi I over 4 for the square root of minus I. And so if I put those back into here, I'm back where I got to the other way. And then if you multiply this out, it's kind of interesting that, the reason you probably wouldn't be able to factor x to the 4th plus 1 directly, high school algebra style, is that you'd have to somehow see that this factors to that, which maybe is not entirely obvious, right? But there it is. Any quartic can be factored in theory, right? And here's how it actually goes, but all right, anyway, just a fun fact. Example 7, to solve w cubed equal to 27, and also factor w cubed minus 27, so I have the third root of 27 is 3. All right, that's my principal third root, which is just ordinary pre-calculus in this case. And so this is the third roots of unity. I multiply, to get 27 to the 1/3 power, I multiply the third roots of unity by my principal third root of unity, which gives me this, this, and this, which means I can use the factor theorem to get that, and I get that. And then finally, we have example 7, example 7 on page 8, I should say, where I go through the steps of deriving the quadratic formula by completing the square and taking the square root, the principal square root, right? Well, these are the second roots of that number. And here I'm assuming a, b, and c are complex numbers, but the steps still make sense. All the way up to the plus or minus, because plus or minus is what the 1/2 roots give you in this context. And so here's a specific example of that. If I had this is my quadratic equation, I get this a, b, and c. Here's the discriminant, here's that quantity inside, well, here's the thing inside the square root, which ends up giving me this, and if you sort through it, I get z is minus 1/2 plus or minus the square root of 1/2 plus the square root of 2 minus the square root of 2i. So the quadratic formula still makes sense for complex polynomials, but to be more explicit, you'd actually have to put this into polar form, and then you could calculate it. Unfortunately, I ran out of time to do that today, so my apologies. Do send me questions if you got them. So thanks, guys.